to the lecture.
So I was asked to speak to you for the next 40 minutes about the technical principles underlying AI for radiology, and in specific machine learning and deep learning for radiology. And I'll try to do that without getting too technical. So this is a history of artificial intelligence that you may have seen before. It's used a lot. And it gives a rather simplified overview of the history that you've just seen in the previous lecture. First, we had AI, rule-based systems. Since the 50s, these has been used in different applications. Then machine learning started up big in around the 1980s. So machine learning, self-learning systems. And then more recently, these have been replaced by deep learning. Now, in medical imaging, machine learning was not widely used at all until the past few years. So it looks like we have mainly skipped this phase. I started working on machine learning in medical imaging around 20 years ago during my PhD. And at that time, very few people, very few groups in the world were working on this topic. So the computer-aided diagnosis, the CAD community, was using machine learning. But now, only since the last few years, machine learning, and in specific deep learning, is at around 2014, there was nearly nothing. 2017, we were up to 50% of papers. I don't have the most recent numbers, but I would say we're at around 90% now. But so what is machine learning? It is letting the computer learn based on examples. Now, if I'd give you some examples, some pictures, for instance, of lovely Barcelona, and on the other side, some pictures of Rotterdam, the city where I live. And I would give you a new picture taken in any of these two cities. Even if you hadn't been there, you would probably be able to find out which is which. You would look at the pictures from Barcelona and see there's a beach, there are hills, there are lots of spires, there are palm trees. All those features Rotterdam doesn't have. There are also, if there are colorful dragons, it's much more likely to be in Barcelona. On the other hand, Rotterdam has more concrete, more glass, more water, more high-rises. Now, if we teach a machine to learn to recognize the difference between these different pictures, the classical approach would go actually quite similar to what you are doing. We have an input image, we compute descriptive features, we set them out in a high-dimensional feature space and then train a so-called classifier, a machine learning system, typically based on statistics, to find the best boundary that separates the two classes that you have based on their features. And that gives you an output. And in radiology, the features could be related to the density or the appearance or tissue of shapes, of structures, for instance, speculation in nodules. Now here's a very simple example of machine learning, a very basic machine learning approach in radiology. We have just two features, and those features are only the intensity in a T1 and a T2 image. Now if we set those out on the vertical axis, the T1 intensity, on the horizontal axis, the T2 intensity, we see that white matter ends up here. It has a relatively high T1 intensity, relatively low T2 intensity. CSF, on the other hand, ends up here. And now, if we train our classifier, it could give us boundaries like this. And just using these two simple features, we could already get a pretty good separation between white matter, gray matter, and CSF. Now, most problems are not this easy. And even brain tissue segmentation is not this easy if you want to have all the details correct. Now, if we go to a more complicated example, hippocampus segmentation, intensity is clearly not enough. So on the left, you see a zoom in of an MR image with the hippocampus. You should see the structure. It's not very clearly visible, so that's why I also put the manual annotation in the middle. And then if you try to find the optimal intensity threshold that separates the hippocampus from its background, you would get a figure like the one on the right, which clearly is not a very good segmentation. So we need something more. Now, a typical approach is that a typical way to solve this is to extract a large number of more descriptive features. Here you see an example of different scale space features. We have filtered the image with different filters that highlight the local image appearance. For instance, how much the image locally looks like an edge or like a sphere or like a cylinder, and at what scale this happens. And then we can again use a classifier to find the boundary between classes, between hippocampus and background, but now in a more complex high-dimensional space. And that gives you a result like this. So you have here the intensity result on the bottom right and the classifier result using more features on the bottom left. And now if you would only take the largest component that is in the area where you would expect the hippocampus, you have a very good hippocampus segmentation already. Now this is the more classical machine learning approach. Now, in the past few years, we have been replacing this by deep learning. So what is new in deep learning? In a classical picture, we had this input image, we compute descriptive features, we train a classifier, and that gives us an output. And now in deep learning, we take this part and replace it by a neural network. This neural network, it works directly on the original image data. We still apply filters, but we now apply them in multiple layers, which allows us to make more complex features, even more complex than we had before. And very importantly, we don't design these features ourselves, these filters, but we learn the filters. We learn the filter parameters. So this is a very big machine with a lot of parameters. We feed the machine with input images, of which we know what the output should be, input voxels, of which we know whether they should be hippocampus or background. And then we change the model parameters to minimize the prediction error on our training data. And deep networks, even though within radiology maybe they seem new, they have been around for a long time, but they have only in the past few years become really successful, mostly through better use of training data and better computational resources. Now, what can we learn? We have this machine, this neural network that learns the relation between an input image and an output. The output could, for instance, be a segmentation, and then we train a network to reproduce such segmentations, but then hopefully it can do it correctly on unseen images as well. We can feed the network with patches that contain lesions or do not contain lesions, and then if we train the network to make these predictions, to discriminate between patches with lesions or patches without lesions, we can use this for lesion detection. We can also characterize lesions. If we train the network with patches of lesions for which we have, for instance, a biopsy ground truth telling us whether the lesion is malignant or benign. We could even move into diagnosis or prognosis directly, feed the network the complete image and the radiology assessment that this person has atrophy. Or even if we have a longitudinal study and we follow these subjects over time and we know how they develop, we may be able to train a network that can tell you whether this brain, the person having this MRI image, is likely to develop dementia within 5 years or not. We can also put in a low-quality image and learn a high-quality image, and that's what Daniel Rickert will tell you a lot more about later today. So this is a very versatile learning system. And we have seen that deep networks can solve very challenging tasks, very challenging image analysis tasks, very challenging segmentation tasks. So here's just one example. What you see here are intracranial calcifications, so on head CT. We're looking in the area around the intracranial carotid siphon. And what you see here are in blue manual annotations and in red automated annotations made by a deep learning system. This is work by one of my, Gerda Bortsova, one of the PhD students in my group. And this segmentation problem, a few years ago, it was not possible to solve this. The calcifications, you can clearly identify them by their intensity, but on the other hand, they're very close to the bone. They sometimes seem to touch the bone, even in the CT. And that's why you can't easily separate them. So we couldn't solve this before, but now with convolutional networks, we can. We found that we did a large study. We trained this network on around 1,000 training images and tested on 1,000 more. We found that the agreement with observers is in the order of the inter-observer agreement. So here you see some more details of that. You see the precision recall curves and the FROC curve. And what is important to note here is that the star indicates the inter-observer agreement, which lies below or on the curves, which means that the system is at least as good as the observers. We also had an independent observer compare our automated detections, our automated segmentations with manual segmentations made before. And we found that actually in 70% of the false positives of our system, these lesions are actually true positives, but they were missed in the original annotation. And on average, automated annotations were slightly preferred over manual annotations. And yeah, I will show you just a few examples in this talk, but there are really many examples by now where deep learning systems are performing at the level of a human expert in very specific, well-defined tasks. So now you may wonder, how do I choose a good machine learning system? Well, a good machine learning system, a good classifier, of course, makes few errors. And if we have a training set, we can measure that really easily. We can optimize the parameters of our classifier so that these errors are small. But there are many different ways we can make few errors on the example that I show here. So suppose we want to separate our class A and our class B data points in this simple 2D example. This could be one way of classifying them, of determining the decision boundary. But this could be correct as well. And this would give you even fewer errors on the training data. So what is the right classifier to choose? Well, it's quite difficult to say something really general about that. But what is important and what should always be tested is that the classifier should make few errors, but on an independent test data. And we're not really interested in how it performs on our training data. So if we make very complex classifiers that can classify all points in our training data correctly, we have a So a good classifier makes few errors on unseen test data. And it uses the training data, but it does not just memorize it, but extracts general concepts that help it solve the same classification on new data. If we, for instance, compare this classifier, this one here, which can perfectly reproduce the training data or classify points that are really close to the training data, but it's unpredictable everywhere else. If we compare this one with this one, that uses the assumption that points in the neighborhood of our training data probably have the same class, so the neighborhood of blue should be blue, the neighborhood of red should be red, we may expect this algorithm to perform better on unseen data, or even this one. So, important to remember, it is very important to test on independent data, at least from different patients. If you need a technique that can be applied across scan protocols, you also need to make sure that your system sees a variety of scans during training. So this is the typical behavior that you would see of a method during training. It can perform on the training data. The more complex you make the model or the longer you train it, the lower the error becomes. But if you look at the performance on independent data, it also goes down at first, but will then increase later on. So we need this independent data and then decide that here we want to stop training. We always need an independent validation set. Now, if we train on more data, then typically the point where you start making more errors on your validation data is a little bit later, and we can train the model until there and get better performance on new unseen data. So the machine learns from examples. Machine learning fits a model to predict output, image segmentation, lesion type, diagnosis, etc. from the input image. This requires representative, annotated training data. More data typically leads to better models, and high-quality annotated data is difficult and expensive to obtain. Now, one of the things we need to look into is whether we can learn reliable models with less data or low-quality data. So I realize that I'm actually not so used to this node view. So maybe I have shown you some slides that were, maybe I showed them sometimes only later than what I was talking about. I'll try to do that better from now on. But if I do it again, maybe try to warn me. So I think this image really, often, in machine learning, the quality of your training data is really important. And often people will tell you it's garbage in means garbage out. If your training data is not good quality, the end result will not be good quality. And I think this image is a really beautiful example to illustrate that if you treat garbage the right way, you can still get a very nice end result. So we trained a model to segment lungs in the MRI. And we had training data that you see on the left. These were, they were not fully manual annotations. They were made interactively. And the goal at that time was to measure the volume of the lungs. So these annotations didn't need to be extremely accurate. And you see that there are quite a few errors there. I hope you can see it in the back. So there are strange things sticking out of the lungs. There are some parts that definitely shouldn't be there that are outside of the lungs. Now, if we train a regular convolutional network on this kind of data, we get a result like this. Nicely smooth lung fields. So probably it would still be better to have really perfect training data, but it's not necessarily the case that if you have errors in your training data, your end result will also be bad. So if you regularize your models in a correct manner, you can still, as long as the errors on your training data are random, there's not a systematic bias, but there are random errors, you can to a large extent correct for that, because the models smooth out the decision space. Here's another example from a little bit longer ago. The goal was to segment airways in CT images. we trained on data that we could easily obtain, which was made by just a simple intensity region growing of the airways in a lung CT scan. So you start somewhere in the trachea and you add voxels, successively you add voxels that are similar in intensity to the region you've already found. And then you stop when there are no nearby voxels that have similar intensity. And that works fairly well in the central airways. You can find the bigger branches with this, but you will not be able to find more peripheral airways. Now, we trained the system on that. So this was before deep learning. This was a Gaussian filter bank, regular classifier. And the test result looks much more complete than the data we started training on. And this can happen because in our training data, even though we miss almost all of the small branches, it's sometimes by accident we do find them because there's less noise at that location. Maybe there's the start point of the airway is a little bit larger. Sometimes we do find them, and that helps us train a model that can find smaller branches also in other images. Now, if we added more information to this model, in this case, this was vessel context. We know that the airways branch they follow the arteries, they are close to the arteries and branch at the same points approximately. If we put features describing that knowledge in, we can still get much further. And I don't have results on that exact data anymore, but I expect that with recent deep learning techniques, we can model this vessel context directly without needing to put in this prior knowledge ourselves. We can just let the model learn it from the image data. So our training data doesn't have to be perfect. Another way of looking at this is that we could try to learn models from so-called weak labels. And what I mean with that is if the task, for instance, is to segment hyperintensities in MRI images, strong labels would look like this, and they take a lot of time to make. Weak labels could be, there's a moderate lesion load in this image, or there are white matter hyperintensities present in this image, or we have 3 lesions visible in one slice. So such labels are much easier to obtain, and if we can learn reliable models from them, we could much easier on a large scale solve problems using machine learning. Another example that I also show you a little bit more of during this talk, lung CT. Strong labels would indicate the abnormalities that are present, where they are, what type, and how large they are. And weak labels could be, for instance, emphysema is present in this image, or what type of emphysema is present and where it is roughly, or even the lung function of this subject. Now, if we can learn from such weak labels, we can learn from labels that we can obtain relatively quickly, for instance, already available data with semi-quantitative analyses or radiology reports or clinical databases. So it will be much easier to develop AI systems for many different tasks. One example that I want to show you about the weak labels is quantifying enlarged perivascular spaces. So you see here an example of a subject with no lesions, or different subjects, I think, with no lesions on the left and increasing lesions towards the right. So in blue, I indicated the perivascular spaces. They are basically small elongated lesions. They are bright on T2, and they're usually assessed by visual scoring. What I try to do instead is learn from the visual scorings that are already made. Here's an example. So we look at 4 different regions. An expert counts the number of lesions in certain regions and in certain slices, and then we train our neural network to just predict this number of lesions in these regions or different slices. And we found a very good agreement with the expert scores. So what you see here is the performance, so here the inter-observer agreements and our model trained on a large number of scans, and the model is at least as good as the inter-observer agreement. Trained on a smaller number of scans, 400, it performs less good, but still reasonable. So there's still a lot of effort training going into developing the training database for these methods. But these labels are relatively easy to acquire, and therefore it's still doable. The associations with risk factors were very similar for the automated and the visual scores. So it looks like we can use this model for our research and population studies, which is what it was meant for, at least to begin with. We wanted to look into a little bit further what the network has learned. So we already know that it has learned something that correlates very well with visual scoring, but we don't know exactly what that is and whether it really has learned to detect perivascular spaces. So we the right densitometry, and you see that the machine learning can also find clearly a staging difference between it, can clearly recognize the different stages, whereas densitometry was not able to discriminate between no COPD and mild COPD. Now briefly on the potential pitfalls, this one, memorization versus understanding, we have talked about that. That our training data is representative of the target data. Now, you would probably not really expect that if you had this model that was trained to segment a brain, if you feed it with a heart image, you would not really expect reasonable results. But if you give it different examples of MR brain images that to me they look fairly different, to a radiology they may look very, very similar to a radiologist. Our neural networks will have problems with data from protocols it hasn't seen before. So there are ways to overcome this. Here's an example of a transfer learning approach that was developed in my group. We see again a training curve, the amount of errors that a classifier makes if you give it more training data. Now this is, suppose we have a large set of training data that is different from our current scanner and a small set of training data that is from the same scanner. This is what a normal machine learning system would look like. The error would decrease, but very slowly. On the other hand, if you only train on this data from your new scanner, the error would decrease, but in the beginning the error would be really large. And then transfer learning can make a good compromise between these two approaches and have lower errors already in the low sample size regime. And here are some results of that. So, yeah, what you can see is that our transfer classifier can, with very limited training data, find the boundary between white matter and gray matter much better, whereas a regular classifier would not be able to do that. Now there's a risk when using AI that your decisions are biased. So here are some examples that you may have seen before. Early software for speech recognition could not understand women, as it was mostly trained on examples of the software developers themselves, which were mostly men. Similarly, also face recognition in the early stages did not perform very well for everybody and made very painful mistakes. And software in use to predict who is most likely to commit a crime in the future turned out to be strongly racially biased. Also in medical imaging, we may have this problem, and we have to be very careful on what data and what populations we train our systems. Here's one example of our own work on that. The COPD texture prediction example that I showed you before. Our first results, so these are actually much nicer than what I showed you before. Our first results looked like this. The machine learning approach was much, much better than densitometry. And we were, of course, happy with these results, but we thought it might be too good to be true, and we looked more closely into the data that was used to train and validate this system. And we found that in this case there were relatively many women in this database, which makes it more difficult for densitometry because standard density thresholds are used even though women have denser lungs. And apparently, probably, our machine learning system could exploit this correlation, perhaps by looking at the size of lung structures, and then it figured out that women have a higher chance, or people with small lung structures have a higher chance of having COPD. If we carefully balance the training sets for gender, we get the results that I showed you before. So there's still a nice improvement of machine learning, but the difference is not as big as we thought initially. Now, so I think we've seen an example of this before in the previous talk. Has the machine learned to see as a human? No. Here's a great example. 3 very different images. The network can classify them correctly, but if you add a very specific noise, I must say it's a very specific type of noise that is optimized to make this network make wrong decisions. But then if you just add a small bit of noise to us, it looks exactly the same. To the network, these images are all an ostrich. So this is a quite surprising result that it won't happen by itself in practice. It only happens if you really try to trick the system. But it illustrates nicely that the network makes decisions differently than you do, and it also can make errors that you would not expect it to make. So the machine can't see as a human, but it's becoming very good at predicting our decisions. Now, will AI replace radiologists? Maybe in some areas, but I think this slide that I borrowed from the ACR Data Science Institute illustrates really nicely that what we are doing now with AI is solving very, very specific problems. So we focus on quantifying or detecting a specific structure in a specific anatomical region in a specific imaging modality. And this is so-called narrow AI. It can solve specific problems really well, but it can't do anything else than this very specific problem it was trained on. Now, a general AI that can make any kind of diagnosis based on any kind of modality and anatomy, a general AI that could really replace the radiologist, that's still very far away. So to conclude, machine learning and deep learning are very powerful techniques for image interpretation. They are very versatile. They can perform segmentation, detection, tissue characterization, diagnosis, image synthesis, and even more. They can automate repetitive tasks, and they can uncover new imaging biomarkers. And I think the next talk will go in much more detail there. They typically do require training data, a lot of it, and it has to be to some extent representative. It can't deal with situations that are very different from the training data and can be difficult to interpret, although techniques are in development and already exist to make these problems less. I'd like to thank you for your attention.